So today I'm going to be talking about some variation of an algorithm that was, very near and dear to my heart. In astrophysics, we did Markov chain Monte Carlo all the time. I'll get into what that is. But yeah, so the paper I'm looking at today, the authors make an attempt to parallelize this what is inherently a sequential algorithm. So this is one of the more widely cited papers that tries to do this, even though it's a bit older. I still found it to be, a pretty good read, and I feel like I was convinced that they contributed something. So that's always good when you read a paper and walk away feeling that. So here's their abstract. These guys are out of Carnegie Mellon, or they were circa 2013. They give a quick overview of what MCMC is in their abstract. But the key thing that they note here is that, we're trying to minimize communication costs whenever we're designing some distributed algorithm. And they claim, and they will show that they can actually reduce this inherently sequential algorithm to something that is in fact embarrassingly parallel. So we'll get into exactly how they do that, but if you take anything else away from this, that is what we are attempting to do and show through the subsequent slides. So what is MCMC and what are we trying to do? So the core task that we're trying to accomplish is that we want to sample from some distribution data given some data. For trivial functions, there might be some other sampling techniques you could apply. But in general, think of like a loss function in a neural network. If I wanted to express the distribution of the neural network parameters given the data, that's not something I can do trivially. So that's really the motivation here. So MCMC is a broad framework that goes about telling us, a way that we could maybe do that. So from starting from Bayes' theorem, we see that this is a familiar expression probably to every data scientist here, that the probability of the parameters given the data is proportional to the probability of the data given the parameters times this P of data, which is called a prior distribution. And really, in Bayesian statistics, what this encapsulates is our prior belief about what those parameters should be. We note that the special case, when it's uniform, our predictions just degenerate to the frequentist likelihood. So I'll get into that a little bit more in a second. So given this expression, what can we do? How do we simulate this? How do we construct this distribution? So there are a number of ways to create these samples. I'm going to cover one method, which is the Metropolis-Hastings algorithm, which if you've studied MCMC before, you've either seen this or Gibbs sampling, which is a special case of this. So the idea is that we want to come up with some initial guess for the parameters. We'll call that X naught, and I've kind of abused notation here because X was the data in the previous slide, but here it represents the parameters. And then for I in some number of samples that we want to generate, we're going to propose a new candidate by sampling from some dispersed distribution. So say like we'll generate from our current point about the normal distribution centered on xi, and then we'll propose a new xi to enter into the chain. And if a random uniform number is less than the ratio of the likelihood of the current point versus the the proposed point versus the current point, then we'll either accept or reject the new point and either enter the new point or the old point as the next element of the chain. And what this means is that the values of the chain converge on the posterior density distribution that we were trying to estimate in the previous slide. So that's essentially how we go about drawing a sample from this f of data given x. So that's the sequential algorithm. And I think it's apparent that, why this is sequential, because in order to generate the next step, I mean, there's no way I can parallelize that, right? I can only generate one one next step, because the following steps all depend on the previous step. So it's inherently sequential. So let's like take a moment to step back and like try to understand what we're doing a little bit more. And I kind of wanted to like harp more on some of these properties of maximum likelihood that, while that's a frequentist approach, the authors make use of some of the results here, and show that a lot of the same results from maximum likelihood actually apply when their algorithm is applied. So remember that the frequentist likelihood is defined as the product of, you're going to multiply together some number of x given theta, and that's going to be, for example, a lot of the times that's assumed to be a normal distribution. It's important to remember that the likelihood is not a probability. It's not the probability of a particular set of parameters. It's the probability of a particular sequence of observations, or the density in the case of a continuous variable. So what's special about the likelihood is that if we minimize it, we get a single estimate in frequentist statistics for the parameters. In a Bayesian sense, we would be assuming a flat prior, but we don't talk in terms of distributions in frequentist statistics. We just give the single point. Usually it's denoted theta hat. And that point has some really nice properties. So if you are actually minimizing the likelihood, you're guaranteed that given enough data, your estimate of theta will approach the true value of the population parameters. And as the sample size increases, there's actually no other way you can get a lower mean squared error. And it can also be shown that this also means that the distribution, if we to the extent that we talk about distributions in frequentist statistics in terms of estimators, that distribution would be asymptotically normal. So that's like a very important result, because you would think, okay, so if we add a prior to that, then that's no longer the likelihood. So perhaps that property does not hold. And we'll talk a little bit more about that later, because it's actually really important to one of the author's approaches. So let's get into the author's model. So as I mentioned, the process of simulating a single chain is inherently a sequential process. So there's really not a way to go distribute the calculation of a single Markov chain to multiple processes. So what the authors opt to do instead is to aggregate the results of multiple chains. And the way they go about doing this is actually kind of cool. So what they do is they split the data into subsets. They distribute them across multiple basically non-communicative processes, so they have this full posterior distribution that they're trying to estimate, which is composed of what they call a sub-posterior distribution so this is one chain given the mth subset of the data, and it gets or it gets the prior to 1 over the m as its prior. And they show that under some asymptotic assumptions that this is actually going to converge to a normal distribution for any posterior. So the actual theorem states that if as like the sample size x goes to infinity, all posterior estimates under certain smoothness constraints will become multivariate normals, and they actually state in terms of their sub-posteriors what the parameters of that normal distribution are. Great. So what does this look like in practice? So obviously we've made a really big assumption here, which is that which is that like actually the only posterior distribution I can generate given a sequence of samples is normal, the way that they're combining this. So I mean that's obviously pretty limiting, especially if we're not in that asymptotic limit. So what does that mean? So here they do an example of a Bayesian logistic regression, and they are showing essentially that when they these orange ovals are they're subposteriors, and they show that when they reconstruct I think this is a 50-dimensional logistic regression. So these are like the first 2 dimensions. So you're looking at like the marginal distribution in those 2 dimensions. So they show that at least in those 2 dimensions, it looks very well in agreement with the true posterior distribution. So with that being said, it looks like their technique is actually producing the right result. So the problem for things that aren't as nice as logistic regression is that the in the limit of finite data, the posterior might be very non-normal. So you would have to wait until you had infinite data basically to be in that, at that asymptotic limit. So what do we do if, we're not doing something like logistic regression? What if it's like, what if our posterior is very non-normal basically? Well, then you basically have to be very general with your subposteriors. And in fact, what they try on sort of the opposite end of the spectrum in their non-parametric model is they say that their subposterior is a kernel density estimate with a Gaussian kernel. So what they'll do is they'll draw P samples without the hats using Metropolis Hastings, and then they'll use kernel density estimate to combine the samples into a single distribution for that represents the posterior. That is shown right here. And essentially what that comes down to is a weighted average of these kernel density estimates, which you can efficiently sample from actually, and they provide a way to efficiently sample from this distribution down here. So that's really cool. So like let's look at it on that logistic regression model. So here you've got that parametric model where everything has to be normal. The semi-parametric model, which I'll get to in a second. The non-parametric model is teal. And then the other one we'll really want to look at is what happens when we just have a single Markov chain. And they show wall clock time, essentially a convergence of the mean squared error here. And we see that this parametric model, which assumed the normal distribution, actually converges quite quickly after maybe like 400. That's about like 400 seconds. But we're kind of left confused here because this non-parametric, really general model, which should be a lot more prescriptive, has not. It's not converged. It doesn't converge as quickly. So we're kind of looking at this like, well, obviously we kind of want to do something in between these 2 things probably most of the time. Most posteriors that we're interested in are probably, they're probably slightly normal. So what can we do about that? So although the non-parametric model is very general, its constructed density estimate is going to, converge very slowly. What they try is to add this additional weight factor right here in their kernel density estimate, which is essentially the infinite data limit normal distribution. So by adding this weight, if we were to take the limit in which the data went to infinity, the numerator, one of the normal distributions in the numerator would cancel out with one of the normal distributions in the denominator, and we would be left with the normal distribution estimate from the parametric model. So is asymptotically consistent. It's an asymptotically consistent way to combine these samples. So just to recap the three different models that they are sort of proposing here, and the assumptions that they make, all of them start with a sample from the posterior distribution using MCMC. And then this sample is combined either by assuming a normal distribution in the case for both the subposteriors and the posteriors, the full posterior for the parametric. Semi-parametric, you have this normal weighting factor for the subposterior, but you end up with some kernel density estimate product. And the non-parametric is it's completely kernel density estimate, all Gaussian kernel density estimate. So the key differences are just really in the assumptions that they make about the subposterior and posterior distributions. So here's an example of where this parametric model, which did really well in that logistic regression, might fail, and we would want to do something more sophisticated, like with the parametric or semi-parametric models. So here they're basically saying, what if we had a posterior distribution that was a Gaussian mixture model? So in the top left, here is the model that they're just saying this is my posterior distribution. And then here they show some examples of what some of the subposteriors generated from MCMC look like. And then they show these different averaging schemes that we just talked about for combining the chains. So this sub-post average is like they literally take the arithmetic mean of all the subposteriors, and that's how they get this. And that's obviously wrong. There's no theoretical reason to think that means anything. Here's the non-parametric model where they combine the subposteriors and then create the density estimate from kernel using a kernel density estimate. You'll see that it mostly matches the true posterior, except kind of like this area right here where this cluster of points has kind of been merged into a single component. The semi-parametric, I think it gets the locations right, but it's really fuzzy, and that's clearly to do with this assumption that this distribution has to be very normal. And then you see the parametric model, which can only be a normal distribution, is just completely wrong. I mean, there's no way a single normal distribution is going to fit this posterior. So you kind of have these sort of two extreme scenarios where, in the case of logistic regression, we had probably a posterior distribution, which was, kind of even in the limit of pretty finite data, somewhat normal. So the parametric model did very well. But in this hypothesized very non-parametric posterior distribution, where we might have very finite data, and then that model doesn't do as well. And you can see that in the same sort of plot where we're plotting MSE versus time. You see that the parametric model, I mean, it converges instantly, but it has horrible accuracy. And then I don't even know what the arithmetic average even really means in this case, but it also does very badly. The semi-parametric model does well, and the non-parametric model also do well, converging in approximately the same amount of time. So I just like to kind of conclude by saying, I think this is a really useful thing for us to think about, because especially now, I was really intrigued by this parametric model, because think, for example, like hyperparameter searches. Generally speaking, if those distributions are very non-normal, we really don't care, I guess. For the most part, we kind of just want to get in the ballpark of what is generally correct. And this is we also don't want to train, a really long Markov MCMC model that has to evaluate a neural network on the full set of data. So one of the nice things about their approach is that the data set is distributed across the multiple processes. So all of those models are trained on a subset of the data, and in theory should converge faster. So even with 10 processes training, like like a neural network, for example, we could probably get pretty good estimates in a short amount of time with this parametric model for what the best hyperparameters are, and sort of what the trade-offs are between the hyperparameters. And that's kind of what piqued my interest, was like, MCMC is not, it's not, the algorithm itself is not hard. I wrote it on a single slide. And knowing that we can do this on maybe multiple Kubernetes pods, and then combine the result, is something I think we should think about. I think Eric also brought up this technology, Ray, and I don't know what it does to scale, but that also might be worth looking at. But going forward, I think this is a good thing to think about doing systematically, not just as a business, but I mean, it is really what you're supposed to do when you want to deliver models like this, or you want to deliver models and have some confidence that you're delivering the best version of that model.